Oop. Howdy. Alrighty. This first one that we're going to do on the builder is pretty tough-ish. Tough-ish. It's one of those that we did towards the end of classes, where I give you a polynomial. This one's a cubic. And one of the complex zeros, you need to tell me what is the other complex zero, and then multiply those factors together, and then use long division. So tell me what the remaining zero is. I'll give you 3 minutes, and then we'll go over it. Okay, so let's do this piece by piece. If 4, 1 is a 0, what else is a 0? Negative 4, 1. Or 4, 1, 4i. Yeah. So 4i is a 0, negative 4i is a 0. All right. Since those two are zeros, I know that I can write x minus 4, 1 and x plus 4, 1 as 4, 1. What is Tyler? Ty? You just started me on something, and now it's ruined forever. You could write x minus 4i and x plus 4i as factors, right? If I then multiply these factors out, x times x is x squared. X times 4i is 4ix. Negative 4i times x is negative 4ix. Negative 4i times 4i is negative 16i squared. If we combine like terms, 4ix minus 4ix is 9. I squared is really negative 1 times negative 16 is really plus 16. So the reason I do that is because I know these factors multiply out to be this, which, by the way, if you would have said A is x and B is 4, the answer is A squared plus B squared, right? You're multiplying conjugates. But anyway, the reason why we do that is because if those are factors, right, then I should be able to divide them from my polynomial to find the remaining factors. So I'm going to do long division now, where I'm going to divide by my answer. If it helps you when you're doing this long division to think the numerator or the denominator is this, you can, right? Those are the same thing, x squared plus 4 and x squared plus 0x plus 4. Thank you. Hopefully I'm not rustling any feathers with that. It's funny because Russ just came in. And Russ. Okay. All right. Save that. Perfect. All right. So we go through long division. Take my lead terms and divide. 3x cubed divided by x squared is 3x. Multiply 3x times x squared plus 4 would give us 3x cubed plus 48x. No, what? Plus, where'd the 4 come from? Oh, I'm tired today and I don't even know why. It's not a 4. It's a 16. That's why it's 48x. I pulled that from my B value here, explaining that shortcut. All right. When I multiply it like that, does everyone see why I would write the 48x over here and not under here, right? Because of like terms. If you thought like I have a 0x in the middle of this, I would get 0x squared here then. But again, we don't really need to write that, right? It's 0. If it helps you to write the 0, write the 0. All right, if I subtract these then. 3x cubed minus 3x cubed is 0. Negative 2x squared minus nothing is negative 2x squared. 48x minus 48x is 0. And then I drop down my next term, negative 32. And then I repeat the whole process again. So back to the top, I'm going to divide. Negative 2x squared divided by x squared is negative 2. if I multiply -2 by x squared plus 16, I get -2x squared minus 32. Which, would you look at that? As I live and breathe, if we subtract those, we get no remainder. But we knew there was going to be no remainder, right? Because these are supposed to be a factor. It's supposed to divide into it, right? That's why this whole thing is supposed to work. If you got a remainder here, that means you done goofed somewhere. And go goof and hunting. See if you can find the goof. All right. So basically, if I take my cubic and I've removed the 2 zeros I know, it'll leave me with one linear factor, 3x minus 2, which I can then solve to find my last 0. If 3x minus 2 equals 0, then 3x should equal 2. So x is 2/3. Ba 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 ba. Great. The nice thing about that problem is not only is it hard, but it's also fun the whole time. It basically tests everything you learned since chapter 1, lesson 1. Till now. You know how to find zeros? Do you know how to do conjugates? Do you know how to distributive property? Do you know how to do long division? All of it. Your chapter 2 test could just be, here's this one problem plus a graphic problem. I now know you know everything we've talked about. Oh, why did it do that? That's so weird. Don't do that. There we go. All right. Anybody need more time to write? All right. Here's what we're doing today. We already know how to do that. This is new. It is not hard per se. I would say it's probably medium difficulty. It's really just a lot of rules. Each rule is easy. Like each individual rule is super easy. But there are like 5 rules you have to follow to get the answer. Again, each individual step super easy in the process. This is just applying what you learned. So that last part is going to be on your own. There are textbook examples and videos for you to use if you like, but it's just be like, do you want to see more examples? I will tell you, you need to stretch. Stretch out your wrist today, okay? Get that going there, because we're writing so much. We're going to write so much today that you're going to think this is history class or English class. Do you write a lot in English? Like by hand? You mostly typing. Yeah. History, you probably take a lot of notes by hand. Yeah, ish. That was always, I took a lot of notes in the old history class. All right, first one. To be honest, I don't, this first one is optional. There's not going to be any test or quiz questions over this. It's just, do you know how to find out what a rational function is? A rational function can be written as a fraction of 2 polynomials, and the denominator cannot be 0. So for example, you could probably get by with just writing this example. X squared plus 3x minus 5 over x cubed plus 8. That is a rational function. It's got a polynomial in the numerator and a polynomial in the denominator. Okay? All right, this is the first rule that you need, but again, you might already have this in your notes. But if you want to find the domain of a rational function, you need to find the values of x that make the denominator 0. Take those out of the domain, whatever's left is good. Or in other words, the domain of a rational function, the values of x that are valid inputs, are all of the numbers except the ones that will make your denominator 0. That's important, okay? But again, it might already be in your notes. I'm pretty sure we did a bell work over this too, right? Because again, that was like, I think it was on the very first week of class. I was like, hey, there are only 3 things that we're going to talk about in this class that limit the domain. Dividing by 0, square rooting negative numbers, and logarithms of 0 and negative numbers. Miss Ralston has her own little passes. That's kind of cute. She just has these that cut out a whole bunch of. I should do that. I just have note cards. All right. Looks like we're good. Anybody need more time to write? Okay. So for example, can you tell me what is the domain of this function? Or in other words, what value of x can you not plug in? After you've done that, I would like you to do an additional thing. I would like you to graph your function either in Desmos or on a TI-84 and tell me what is happening to f near any values you excluded. Give you 3 minutes. Okay, so what value of x is no good? One. Yes. You plug in one, the denominator will be 0. So I can write the domain. The domain is all of the numbers from negative infinity to 1, not including 1, and all of the numbers from 1 to infinity. Again, not including 1. So negative infinity to 1, union 1 to infinity, parentheses for everybody. Nobody gets included. Not infinity, not 1, just the numbers in between. All right, if we graph this, it looks like this in blue. I have also graphed in green the vertical line where x is 1. So we can see what happens. As x approaches 1 from the left, what does f of x do? So as we approach 1 from the left, what happens to f of x? Well, it goes down forever, right? So f of x approaches negative infinity. As we approach 1 from the left, f of x goes down forever. As x approaches 1 from the right, f of x approaches what? What happens? So we get closer to 1 from the right, f of x goes to positive infinity. It goes up forever, right? That's what it's looking for the behavior. Like we did for end behavior, right? As we went to x went to positive infinity, we wanted to know, does f go up or down forever, right? Okay, makes sense? Questions about that, or does anyone need more time to write? Okay, I know what you're thinking up to this point. Mr. Lake, you said there's going to be a lot of writing today. Not so far. Huzzah! Here you go. All right. So what this section is really about is vertical and horizontal asymptotes. Almost all the homework questions are going to ask you, here's a rational function, tell me all of its asymptotes. A vertical asymptote is a vertical line, x equals some number a, where as x gets closer to a, f of x goes to positive or negative infinity. A horizontal asymptote is the same idea, but flipped. It's a horizontal line, y equals some number b, and as our outputs approach b, x goes to positive or negative infinity. It's just roles are reversed there. For these examples, you could probably just copy down the first two. You don't need to write what the functions are. Just a rough sketch of the pictures is probably fine. If you want to include all three, that's fine, but probably a little overkill. Because again, what I want you to pull out of these pictures is the behavior we're talking about. So for example, if we look at this first one, this vertical line, x equals -1, is an asymptote because as we approach it from the left, f of x goes to positive infinity. And as we approach it from the right, f of x goes to negative infinity. The horizontal line, y equals 2, is an asymptote as well, because as we approach it from above, x goes to negative infinity. And as we approach it from below, x goes to positive infinity. You can see in the next example be that there is never any vertical asymptotes because f of x never goes to positive or negative infinity. It does have a horizontal asymptote of y equals 0 because as our outputs get closer to 0, x goes to negative infinity on the left and positive infinity on the right. I know what you're thinking. Mr. Lake, that's great. I understand what they look like, but how did they come up with these numbers, -1 and 2? Did you prepare a slide that could show us how to get those numbers? And would it, if you could, have a whole bunch of words on there that I would have to write down in a short period of time? And yes, I got that for you. Mr. Lake is very accommodating. I was awarded, I don't know if you saw it in the yearbook, if you go to the teacher accolades, Mr. Lake was awarded the most accommodating teacher at Topeka West. Just always giving students what they asked for. Most teachers, they'll get emails from their students. Hey, can I have more homework, please? The assignment you posted was too short. Is there extra problems I could do? And the teachers will go, no, that's unnecessary. But Mr. Lake gives the people what they want. Actually, hopefully they're not bad. I feel like. I think this assignment is slightly shorter. I think I talked one point about making the assignment shorter. The next assignment is super short. It's 4 questions. This one might be a little, the number might be the same, but the problems are quicker. I feel like. I felt like that when I was looking at it. Maybe you're going to tell me a liar, liar, pants on fire. But. All right, are we good to move on to the next one? Teresa, a little bit more time? Nope. Ready? Hot dog, let's do it. Look at all those words. There's so many. All right, this is the last thing going in your notes, though, besides examples. Okay, so here's how you find asymptotes. Again, if you can abbreviate this, that's fine. I probably wrote this out in full. You probably don't need to write every single one of these words. But if you want to find vertical asymptotes, what you need to find are the zeros of the denominator. And here's the big thing. This is going to determine whether or not you get these answers wrong or right. When you're doing it in WebAssign, you're going to get X's sometimes. And I bet you the reason why you're getting an X instead of a green check mark is this last requirement, that don't divide out. That's huge. For example, let's just look at a really simple function. F of x is equal to x minus 1 over, I don't need parentheses there, over x times x minus 1. This function has 2 zeros, right? It has 0 and positive 1, right? This first factor, if x is 0, you got a 0. For the second one, if you plug in 1, 1 minus 1 is 0. However, only one of these is a vertical asymptote, and it is 0, not 1. The reason why 1 is not a vertical asymptote is because I could cancel this factor out with this factor in the numerator, right? They're both x minus 1. I could divide them out. I can't do that with x. There is no x factor in the numerator. X factor. That's a show. So this is a vertical asymptote, and 1 is what we would call a hole in the graph. It is not in the domain, but it does not cause the going to infinity behavior. Okay, so that's how you find vertical asymptotes. You look for the zeros in the denominator that don't divide out with the numerator. To find horizontal asymptotes, here's what you need to do. You need to compare the degrees of the numerator and the denominator, their largest exponent. If the denominator is bigger, the horizontal asymptote is y equals 0. If the numerator is bigger, then it has no horizontal asymptote. And if they are the same, then you have to divide the leading coefficients of the numerator and the denominator. There is a mildly useful acronym to help you remember this set of rules. It is Bobo, Botan, Eats, DC. I know what you're thinking, Mr. Lake. That is not useful to me at all. This is how the acronym works. If it's bigger on bottom, the horizontal asymptote is 0. Bobo. Bigger on bottom, it's 0. If it's bigger on top, there's none. There's no horizontal asymptote. Vine. If the exponents are the same, eats, see, exponents are the same, then you divide the coefficients. Bobo vine eats DC. So some really quick examples. If you had x over x squared, its horizontal asymptote would be y equals 0. If you had x squared over x, it would have none, or does not exist. If they were the same, you had like 3x squared over 2x squared, so that they're the same, its horizontal asymptote would be 3 over 2. Again, if it's bigger on bottom, then it's y equals 0. If it's bigger on top, then there's none. And if the exponents are the same, then you divide your coefficients. Here's how I like to remember it though, is it's a race, okay? If you think who's the first one that's gonna get to 1,000,000, right? The denominator, if it has a higher exponent, 1,000,000 squared is so much larger than 1,000,000, right? Like the number of zeros you have is just incredibly outpaces it. So that forces it, the denominator gets bigger and bigger and bigger, and the numerator gets smaller in comparison. If I have, you think like you're doing a party, I have 20 pizzas, but you keep inviting more and more and more people, right? Eventually you get to the point where basically nobody gets any pizza, right? If you flip that, however, and put it on the top, if I buy 1,000,000 squared pizzas for 1,000,000 people, right? There's basically no limit. Everybody just can have as many pizzas as they want. I have so many pizzas. I have so much more pizza than I have people at this party. And if they're the same, then what's going to duke it out then is the coefficients, where I divide, and that's how many pizzas everybody gets. If I buy 3,000,000 pizzas for 2,000,000 people, again, they're both being squared by the same amount, so the ratio stays the same as 3/2. That's how many pizzas everyone gets. Next time, in an attempt to be healthier, I'm going to talk about salads instead. See if I don't. Next time I do this. If I don't, say, Mr. Lake, you were supposed to talk about salad. I'll know what you mean. Okay? All right. How are we doing on writing? Are we about halfway done? More time? Done? Okay. Yay. Y'all, you just gave me. You don't have that already. You got the important stuff. Yeah. Doing over here? Good. Teresa? Good? Sure. Okay. If, by the way, I am going too fast and you don't want to hold everybody else up or anything like this slide is in the Google Classroom. You can get it, copy down every word to your heart's desire. All right, we're going to finish with one more example then, and then that's the end of class. So let's find all of the asymptotes of this one. No, I take it back. Let's do this one. No, this one. I don't know. No, let's do this one. Let's do this one. I'm committed. I'm committed to it. All right, to find vertical asymptotes, what do? Look at my notes. I set the denominator equal to 0, right? All right, so 3x squared plus 1 equals 0. Subtract 1, 3x squared equals -1. Divide by 3, x squared equals -1/3. Uh-oh, if I square root this, square rooting a negative means I'm going to have an imaginary number, so there's no real solutions. So this has no vertical asymptotes. Okay? It's impossible for the denominator to equal 0. For horizontal asymptote, what's the degree of the top? 1. X to the first is the highest power. What's the degree of the bottom? 2. X squared is the highest power. If we're bigger on bottom, then the horizontal asymptote is y equals 0. Done. This function has no vertical asymptotes and one horizontal asymptote. Y equals 0. Yay! All right, there are more examples if you want to look at the notes. There are some practice problems you can try with the answer listed to what they are in the notes. And of course, you can, watch the videos, read the book, all that good stuff. All right. Have a good one, everybody. I'll see you Monday.